Next talk up is by Amir, who has been looking into why privacy-preserving protocols sometimes do not work so well as we would expect. So Amir, please take it away.
Okay. My name is Amir, and this is a joint work with Andy Rock, Stefan Schiffner, and Thomas Engel. I will first talk about our introduction, and then I will move on to threat model, and then I and our attacks and evaluation, and finally I conclude our work. Introduction: electronic toll collection or ETC market size is forecasted to be $16.65 billion by 2029. And there are several benefits of ETC systems. For example, they help to reduce operational costs, they help to reduce traffic congestion, and they provide seamless payment, and they also help to save fuel. Given these benefits and quite large amount of money that goes into such systems, it is very important to provide privacy and security for drivers in these systems. Two important post-payment ETC technologies are as follows. First, road infrastructure-based ETC systems, where we have different components like toll service provider, RSU, vehicle, OBU, camera, and drivers. And the other technology is autonomous device-based ETC, where we have the similar components while we have here GPS and there is no any RSU here. In our work, we focus on the first technology, which is post-payment road infrastructure-based ETC, where we have a toll service provider and where a user registers into the system by, let's say, providing his, let's say, a copy of his passport to the toll service provider, or let's say a social security number. And in return, the user will receive a unique ID by which the user can be identified in the system. Whenever this user passes through a toll station, the OBU inside the vehicle will interact with RSU, and typically an encrypted version of this ID will be sent to the RSU, so no eavesdropper can learn this ID. And then from time to time, this information inside the RSU will be sent to the TSP, and the TSP will update the user's information, including the amount or the toll fee that the TSP owes, that a user owes to the TSP. And finally, the TSP will issue an invoice showing the total toll fee that the user owes to the TSP, and the user will pay the toll fee. This system is not inherently privacy preserving because the toll service provider records the user's ID, and the TSP can track vehicles. So there are several privacy concerns regarding these systems. The TSP stores sensitive information in order to charge drivers, including time and locations, home addresses of drivers, and total toll fees. This sensitive information can potentially lead to several privacy concerns. For example, the TSP can learn about drivers' movement patterns. The TSP can learn places of interest of drivers, and also the TSP can deliver these data sensitive information to third parties like, let's say, insurance companies. So to handle these privacy concerns, several privacy preserving ETC schemes or PP ETC schemes have been designed so far, like P40C, SpecTRE, private cache, etc. Privacy preserving ETC schemes or PPETC schemes aim to disclose only the minimal information to the TSP so as to build drivers. This minimal information is crucial and unavoidable for the functioning of post-payment ETC systems. For example, P40C, which is a PPETC scheme, leaks the following data to TSP and home addresses. This data should be leaked to TSP during the registration phase by the users, because the TSP should know to whom it should send the invoice. Another information that should be really that should send to TSP and reveal to TSP is total toll fee, because the TSP should know how much a user owes to the TSP, and anonymous locations and times also should be revealed to the TSP. This information is inherently recorded by the RSU. So we pose the following research question. Does a privacy preserving ETC scheme or a PPET ETC scheme that leaks only minimal information ensure privacy in a real world scenario? Given that additional background information or auxiliary information is available in the system, such as pricing scheme, that is a public information, or road infrastructure information that is also publicly available, and statistical data about driver behavior? The answer is not always. These systems do not necessarily guarantee privacy. And to demonstrate this, we provide a counterexample using the case study of Brisbane's ETC system. So our threat model is as follows. The adversary is passive. The adversary is weaker than TSP in the sense that the adversary in our work uses less information than the TSP. The adversary can, for example, be a payment service provider like Apple Pay or a bank of a TSP's customer. So the adversary accesses the following information: toll prices, the graph of the ETC system, including the location of toll stations and their connections between them, the total toll fees, and home addresses of drivers. So to perform attack, we first define a goal for the adversary. It is called toll station disclosure, or TSD goal. It means that the adversary is interested in learning the toll stations that are visited by a driver within a billing period, let's say a month. So, for example, you can see that this vehicle visited toll station A, then toll station B, and then toll station C. And also, the adversary interested in the corresponding frequency. It means that how many times these toll stations have been visited. So it is denoted by the set of trace, including the toll stations and the visited toll stations and their corresponding frequency. The attack is based on solving the subset sum problem, meaning that, for example, here the P is the multiset of toll fees, like $2, $4, etc. And W is the total toll fee that is paid by the end of the billing period by a specific user. And then the adversary wants to know which combination or which sub toll fees inside the set has led to this total toll fee. There can be several solutions. For the numbers which are in red actually are the answers. For example, it could be the summation of 3 and 5 that has led to 8. It could be the summation of 2, 5, 1, or etc. So among these solutions, only one of them is the correct one. let's formalize our attack. So the adversary solves the subset sum problem easily by solving this linear equation, where each term is the multiplication of the toll fee and its corresponding frequency. Then the adversary obtains the solutions and filters the solutions, remove the bad solutions, and finally the output is plausible traces, including the candidates for a correct trace. Among these traces, only one of them is the correct trace that is made by a driver. And adversary easily just uses a simple strategy, uniformly randomly select one of those. And so the success rate is calculated by 1 over the cardinality of the set, which is 1 over D. And interestingly, using a weak adversary, using a minimal knowledge, and using a very simple strategy, we could achieve the high success rates that impact a large number of drivers in Brisbane scenario. We can see regarding the the total fees between $1 and $10. There's almost all the success rates are 100% for regarding the toll fees between $10 and $20. Half of the success rates are between 50 and 100%, and the other half is between 7 and 50%. So we conclude that merely applying such privacy-preserving ETC schemes to current ETC infrastructure does not necessarily guarantee privacy. And we demonstrated this by a counterexample using the case study of Brisbane scenario. And I highlight again that these high success rates are achievable using a weak adversary, using minimal information, and using a very simple strategy. And these are additional results. If you're interested, you can refer to the paper. Thank you.
We have time for one very quick question. Very good. I love it.
I was wondering about your subset something. You were saying that there are multiple plausible options. So I was wondering if the toll system was set up such that the number of unique toll amounts, instead of it being $2, $3, $5, and so on, if the tolls were all $2, would this problem still exist? Like if, in the extreme case, or you reduce the number of unique amounts?
Yeah, that's a good question. Yeah, in our paper, we demonstrated that we analyzed for different distribution of toll prices, and we demonstrated that when the toll prices are equal, it's the worst case. I mean, the success rate of adversary will be reduced significantly. Yeah.